Okay, thanks for that introduction. And I'm going to give you a little overview. It's kind of a vision for where I think high resolution hydrologic observation and modeling are going to go in the future. I'm going to talk about some basics of the global water cycle observations, and a potential water cycle mission in the future, hyper resolution land modeling, and then advanced integration of models and observations that's known as data assimilation. So first, why do we want to study the water cycle? And I'm going to put the energy cycle here also because of the first reason. Water exists in all three phases in the climate system. So as it changes phases between solid, liquid, and vapor, it releases or absorbs a lot of energy, moves a huge amount of energy around the global system, and it regulates energy balances. I think climate change there. Water has a big impact on the evolution of climate change and how that might happen. So water vapor in the atmosphere is also the principal greenhouse gas. So that has a twofold thing. When you increase the temperature of the atmosphere, you increase the ability of the atmosphere to hold water vapor, and therefore you have a positive feedback or possible positive feedback with climate change. But also clouds have an impact. So when you put more water vapor in the atmosphere, you can have more clouds, and they actually tend to cool the planet. So we don't know quite which one of these is going to win, whether it's going to be water vapor as a greenhouse gas or in clouds, either warming or cooling the planet. Water is also the ultimate solvent, so it mediates biogeochemical and element cycles, and water directly impacts and constrains human society and its well-being. So water impacts everything from food, energy, the way that we transport large items. It really, if you notice, most big cities are actually somehow next to the ocean or a large water body, and there's a reason for that, because people and water are kind of inseparable. This is just a picture of when I talk about the water cycle, I'm talking about the oceans, ice, atmosphere, and land. Although I'm principally a land surface hydrologist, I've tried to concern myself about the entire system. So let's take a look at IPCC, the Intergovernmental Panel for Climate Change. These are projections that have been made of climate change from the 2007 report over the next 300 years. And these are temperature changes from an ensemble of different models. So these are all kinds of different models that are run all over the world to predict climate. And they show between a 2 and a 4 degree increase in temperature. But if we look at the precipitation, this is the one I'm more concerned about, is precipitation from this ensemble also increases. So as we expect with more warmer atmosphere, we'd expect more water vapor to be transported around, and we expect precipitation to increase. But look at the distribution here. It's about twice as large, the uncertainty on how precipitation will change as temperature. And this is from the old report. There was a new report that came out in 2014. And here's some pictures from that. It hasn't changed that much. This is the change in average precipitation. This is observed 1986 to 2005, and then this is 2081 to 2100 predicted by the models. So you see some very large changes in precipitation, especially in the tropics and the poles. So it's not evenly distributed. In fact, generally, you tend to get the dry places getting drier and the wet places getting wetter. So the extreme is getting more extreme. This is the observed change of precipitation over land the entire last century, and this is just like the last half century, and you can see the change has accelerated in the last 50 years or so. Okay, so this is some quotes from a colleague of mine, Jay Famlietti, who's now at JPL. He used to be at UC Irvine. But he was trying to shock the federal agencies into actually doing something about the big water problems that we have even in the US. And he says, the fact is we don't know how much water is stored in lakes, reservoirs, streams, and groundwater systems, or even snowpacks. And if you're going to manage any kind of a resource, the very first thing you need to know in order to manage it is how much of it there is. And I mean, if you asked even our federal agencies that keep track of snowpacks, how much snow is there in total, they wouldn't be able to give you a number even within 10%. So it's difficult to manage that. Similar with groundwater, we simply don't know enough about the subsurface and how much groundwater is stored. Further, our hydroclimate modeling assets are simply not up to the task of addressing our most pressing issues of food, energy, water, and national security. We don't have models that can systematically integrate all the observations and give us great predictions of what's going to happen in the future. I got to experience this just yesterday when I was coming here, getting on the airplane. I was getting all these warnings saying your airplane flight might get canceled. Well, we were getting warnings in the mid-Atlantic of a huge snowstorm that was going to hit in the last couple days. And I woke up yesterday morning, and there was about an inch of snow on the ground, and we had been forecasted for much, much more than that. And that happened, the same thing happened 2 days before that, where we just got rain. And these things are hard to predict inherently, but our models and our capabilities of predicting them just aren't where they really need to be. We're spending huge amounts of resources preparing for things that aren't happening. And then I heard on the news on the way to the airport yesterday is that we quote dodged a bullet. And what does that mean? You know, the fact that your forecast was wrong is something to celebrate. And so this is common. We just can't do a very good prediction of precipitation even a few hours or a day in advance. We can do temperature much better. So here's an example of this. This is actually a 3.5 month lead, 3.5 month lead precipitation and temperature forecast that NOAA produced. I think this is GFDL. And this is the skill score. So the higher the skill, the more skill, the better it is. So the redder the color it is, it means you actually have skill. Blue is actually negative skill, whatever that means. I guess they predicted opposite of what would happen. But if you look at the temperature, there's quite a few places where there's not much skill at 3.5 months, but quite a few places in the tropics where you actually get some nice skill. Precipitation, on the other hand, has virtually no skill or negative skill at 3.5 months. So if we want to really do a good job of addressing some of these big issues in food, energy, and water security, we've got to improve this. We've got to get precipitation forecasted at least as well as temperature and improve the whole system's ability to forecast. How do we do that? Will be a question I want you to ask, and I'll try to give you an approach. So water is really important. The projections in the future that we'll have issues with, this is regardless of changes in population, which might have an even bigger effect, but just climate. We're expecting stream flow decreases, groundwater recharge decreases, electrical production by hydropower decreases, increases in disease related to water, and increases in flooded areas and increased pollution. So big issues. So I want to give you some warning. Is one of the things that I do is I like technology, I like fancy things, and I like to solve problems with them. So this is my kind of mentality about how I go about doing my work. Is there's critical problems like predicting the weather or precision agriculture and doing a better job at growing the food we need given the resources we have. So to address those problems, I tend to build up a system. So the system requirements are given to you, but I like to build observational systems, satellites, and ground-based systems. I like to build models that can integrate that information and run them on big computers. So this can be fancy, and some of the things that I'm going to show you are fancy. So I want to give you an analogy, and just to warn you that not everything necessarily needs to be fancy. So in the DC area, when I'm driving around, and probably is happening here too, is I'm not allowed to use my cell phone, texting and driving, and now I'm not even allowed to talk without a hands-free device. My hands have to be on the wheel, otherwise I can get a ticket. So I've invested over the years, because I drive a lot. I live in Maryland near Baltimore, and I drive down to Fairfax, Virginia. It's a long drive around the DC Beltway. And I end up talking on the phone a lot, and I've invested over the years in different kinds of devices like this. And Bluetooth is, of course, the new thing that I have several versions of now. But there may be a better way or a simpler way to solve this, and this guy's figured it out, I think. He's found a way to adapt his technology to the problem without all the fanciness. So in some cases, you might sit back and say, hey, Paul, this is all nice and good ideas, but hey, I think there might be better ways to do this, simpler ways, cheaper ways. So keep that in mind that I sometimes go for the fancy solution. Okay, so now the next thing to do, we care about water. So what are the questions? What kinds of science do we want to do with water? Well, these are some old reports, but the questions have remained the same, is we want to understand what causes water cycle variability or extremes. We want to see if we can predict those variations. And then we want to see how the cycles are linked, how the water and energy cycle and the carbon cycle and the different processes that govern the Earth's system, how they work together. So, so the way we do this, we approach science by this kind of flow chart here, where we start with observations and analyze those observations. New science always starts with new observations. So that has to be the foundation. But then once we get this new understanding, we need to build models to test it and predict new things. So modeling is the second big piece. And of course, we're doing this for a reason, not just to build models, but to actually come up with solutions to society's issues. So we've got to make that final linkage to apply and make a difference with our science. So I hope you can memorize this chart. There'll be a test at the end. Nobody laughed. Okay, so this chart is all of the different variables. So I showed you that first cartoon about the water cycle. Now I'm putting it into variables and words, and I'm doing this for a reason. So this is I've divided this into ocean, land, and atmosphere. And then I've also divided this into what we call internal or state variables. These are storages, like how much water is in the ocean, how much water is in the lake, how much water is in the groundwater. There's also forcing or feedback variables. This is how much moves from one reservoir to another. So for instance, runoff or precipitation is a movement from the atmosphere to the land of water. So it's a very temporary transfer. There's not much storage there. So then I've coded these into blue are actually real water variables, things like precipitation, snow cover, clouds, ice. And then the red are closely related energy variables like surface temperature or geothermal heat flux, radiation, sunshine. And then the plants have a big impact on how water moves around. So I've had to put in some carbon cycle variables that have to do with plants and biomass and leaf area index, carbon and nitrogen. And then in the black, I've put in variables that are kind of our boundary conditions, like topography or sediment transport, deforestation, land use, things that we just need to know about, but aren't necessarily variables. So then down here, I've shown you some equations, and I don't want to overwhelm you too much, but I've overwhelmed you with this chart. Part of the reason is intentional, is how do you possibly know everything you need to know about the water cycle? And the way we do that is we can relate the pieces to each other. So we write equations. And here's an equation, for example, and all this is saying, this is the equation for the water. It's way down there in the corner, right here. This is the equation for water in the atmosphere. If you take the atmosphere as one big bucket, basically what comes out of the atmosphere, which is precipitation, and what goes into the atmosphere have to balance with how much is stored in the atmosphere. And that's this Q term, the storage in the atmosphere. So it's a pretty easy thing to solve, and we've been doing this with some of our NASA data sets to try to see if we measure precipitation, evaporation, and water flux, does the equation work? And we found that it works okay, but we're missing a whole bunch of water just because of the errors in the different terms. But as we get better satellites and better models, we can minimize those errors. These other equations are just equations for other parts of the system, like the ocean and the land. Okay, let's talk about scale. So I talked about hyper-resolution. What does that mean? If we look at variability in the Earth system, we have variability for different kinds of processes. Topography-induced, kind of vegetation or land cover-induced, and weather or precipitation-induced. And you can see, depending on what scale we look at and what process we're looking at, there's very different kinds of scales that these occur over. So topography-induced can be quite fine. You know, you just walking up the stairs, I'm seeing a difference in the elevation and how it impacts the land cover or whatever. The land cover varies on a somewhat larger scale. And then the precipitation is like weather scales, like either convective, which is about 10-kilometer resolution, or frontal, which is about 100-kilometer. So for most of my career, I've been modeling with the LDAS systems, the land data assimilation systems, the US at about a 1/8 degree grid cell resolution, which is nominally about 10 or 12 kilometers these, at these latitudes. So if I drape an 1/8 degree grid cell over the landscape, this is a mountainous landscape. I hope you can see that. Um, I have a lake down here. I have a mountain here. I have some agricultural areas over here. The 1/8 degree model or observation is going to be an average over that period, that area. So if I'm managing a ski resort at the top of this mountain, or if I'm managing this reservoir down here, I'm not going to be too happy about just getting an average because it's going to be not representing what I'm trying to manage. So in reality, I've got to go to a much finer resolution than 1/8 degree to actually get information that people can use in those systems. Okay, so let's talk about the observational piece. This is going to be a three-pronged approach for the hyper-resolution. The first one is observational. And of course, I said observations drive new science. They drive new understanding through analysis of observational things we see. They help us to develop and validate models. And then they help us to make better predictions through initialization and assimilation, which I'll explain in a bit. And then they also help us monitor consequences and validate whether we've done a good job understanding, modeling, and predicting. Okay, so in the water cycle, we can use all kinds of different wavelengths. This is the electromagnetic spectrum. This is the visible light that we can see. And there are things that we can see about the water cycle in the visible. For example, we can see when it snows, there's a huge difference in the albedo. It gets much brighter. We also can see, say, when a soil or a sidewalk gets wet, it gets darker. So we can see some water in those areas. But actually, a much more powerful way to measure the water cycle is with microwaves. So the reason for that is the water molecule. Here's a little cartoon of the water molecule, an oxygen and 2 hydrogen, that happen to be offset a bit. So we have a net positive negative charge that causes this water molecule to do wonderful things, like respond to microwave signals. This is why your microwave oven works, is that the microwave signals actually get absorbed by the water molecule and make it go faster, thus warming up your food or your drink. So we can use those in remote sensing as well. We do use those, specifically to do rainfall, ice and snow, soil moisture. We can actually do some ocean and cryosphere things too. But there's two different kinds of microwave sensors we use. One is an active and one is a passive. So the passive is just observing what's ever there. The active is a radar that essentially sends out a pulse and sees what comes back. And there's a couple different kinds of radars we use. This picture here is a picture of what we call the A train. It's just happens to be a bunch of satellites that are all flying in a similar orbit. And it lets us do some neat things by comparing the different wavelengths and measurements that are made by the different satellites. Well, it happens that we're starting to develop a W train or a water train. I'm not sure what A actually stands for. I think it's the AM train. It happens in the morning. But the W train is potentially GPM, the Global Precipitation Mission, was launched about a year ago, last February. Tomorrow, we're going to get the SMAP mission hopefully launched from Vandenberg. I've been working on SMAP and Hydros for most of my career as well, so it's finally good to see that launching tomorrow. It'll measure soil moisture. And then there's various other sensors that have been up some for a long time, like TRIM and the SMOS sensor from Europe, measuring soil moisture and ocean salinity. And we potentially will be putting together in the next few years a train of satellites all measuring the water cycle at the same time. So that's very exciting and lets us propel some of the research I'm talking about. Okay, so a future kind of post-GPM vision is to do a water cycle mission. So this would observe water molecules through the atmosphere and land or ocean surface using active-passive hyperspectral microwave instrument. So one instrument that can measure many different wavelengths currently that we're flying on a whole bunch of different satellites, we could put on one satellite and measure the entire column from one platform rather than measuring it from a whole bunch of different platforms. And that lets us, that's the reason why I showed you all those equations, is that if we could actually observe all of the different parts of the water cycle at the same time, we can solve the equations. We can get value-added information if we make coincident observations of precipitation, soil moisture, snow, and groundwater and all that. One of the issues is what resolution do we need? And it turns out for different things, you need different resolutions. So there's some like groundwater that we might not need more than about monthly 50-kilometer resolution, but there's some things like lakes and rivers where we need daily or even hourly tens of meters resolution, just because rivers, a lot of them aren't very wide, so we have to get measurements that can get to those scales. So that's a bit of a problem, designing a satellite that could measure all these different scales simultaneously, but not out of the question. Okay, so this is just a bunch of words that is basically what I just said about the potential of developing a new water cycle mission. It turns out that I have some friends in China who have gotten a water cycle mission for China into a phase A, which is the first formal work plan of the feasibility and studying how to do this. So they've put together 3 really interesting instruments that are each mature, but they put it onto one satellite, so they can do active and passive from L-band all the way to 150 gigahertz, which is going to be able to measure most of what I'm talking about. So it's exciting to see at least someone going the first step with this. And I'm on the science team. I hope that they get to the phase B and C, but they're in competition with other missions that might be more glamorous that are going to Mars or the moon or whatever. So that's a lot of it will come down to to politics. Okay, so another issue is antennas. So this is the SMOS antenna. It's a 6-meter antenna. It's quite a large structure in space, and it's called a thinned array because it's approximating what a dish would see, but it's not a full dish, and it's easier to deploy and easier to launch. So this has been in space for about 5 years. In the future, we're going to need much larger antennas. So microwave energy, very long wavelengths, and it tends to need much larger antennas in order to collect the information at higher resolutions. So NASA has been actually developing technologies like this, which is an inflatable technology. These are also inflatable technologies that could be used to deploy very large antennas in space economically. And some of these have been reached higher levels of technology readiness through demonstrations in space experiments. But like I said, with this W train, we might be able to actually do this now. So some of these satellites like SMAP and SMOS and GPM, they don't have all the exact same orbit, but they occasionally will cross orbits and fly past each other. So when that happens, we'll get a point where we get lots of observations all at one time. So we could demonstrate the ability to retrieve multiple water cycle variables from the remote sensing microwave data using some of the existing sensors. One of the challenges is that we don't actually have theory to support multivariate water cycle retrievals. Most of our missions have been focused on a single variable: the precipitation mission, the soil moisture mission, the ocean salinity mission, the snow mission, things like that. So when that happens, we end up with developing retrieval. These are mathematical algorithms that allow us to turn whatever the satellite sees into a geophysical parameter on the ground. And that theory just doesn't exist. So if we started from those water and energy cycle conservation equations that I showed you earlier in that table that I told you to memorize, and we use some conventional but linked forward models. So we have a model for a water variable or energy variable or a flux variable, and then we have our set of observations, and we can iterate and invert until, if we have enough observations, and you know the mathematical problem that you need as many observations as you have unknowns. But if we use lots of satellites, we probably can do this and retrieve all of these water variables in a water balance context simultaneously. So this is an actual proposal I have right now, trying to get this concept funded so I can demonstrate it. It's also possible that a different kind of technology will come to bear, and we won't have a great big single instrument to do this. It might be some sort of a continuation of a constellation. It might be a sensor web. So it's possible to actually fly small bits of an antenna and have them all correlate their information to put together larger bits of information. So, so that's a possibility for the future, is a smart sensor web. Okay, now I'm going to move on to the modeling, the high resolution modeling component. So the problem that we have is that we divide the world up into little boxes, and we model each of those boxes with physical equations that relate parameters to each other. And those boxes are somewhat governed by how big our computers are. And at least on the global scale, those boxes are kind of on the order of, the highest resolution operational models are on the order of about 10 kilometers. They lose some information about rivers and storms and whatnot. And in order to get down to the resolution that we might need to resolve processes, which is probably in the order of hundreds of meters, it might take decades. So are there ways we can go faster than that? Can we cheat? Can we take a breakthrough approach? One breakthrough approach is called superparameterization, and some people are looking at this, where you parameterize a subgrid cell with statistics. So you don't explicitly model the patterns, but you model the PDF, the probability density function instead. Another approach that I'm taking is to actually run the model offline. So you run it not coupled to the atmosphere in terms of the land, and then we can take advantage of an embarrassingly parallel problem that most land processes are one-dimensional. So you don't have to know, say, the soil moisture in Nebraska in order to solve for the soil moisture in Maryland, because they're just not that well correlated. But if you want to understand weather, you actually need to know the weather in the two places and how they're correlated in order to solve that. So we can take advantage of the decoupling of hydrology and solve some of these processes offline and take a few jumps ahead of the fully processed coupled models. So in terms of the land surface, I'm going to revert more towards the things that I do with land surface hydrology. We have a conceptual cartoon of how the land works. And you'll notice a lot of processes here, a condensation and advection in the atmosphere. You have some horizontal movement here. You have runoff and groundwater, root uptake, plants, evaporation. You essentially have weather generating processes, water resource processes, and then also biogeochemical cycles, the plants. And you notice that all of these they look continuous, and they are continuous in the real world. But in our modeling, we divide them up into subroutines because it's easier for us to compartmentalize. And so we'll take the groundwater and we'll put it in one set of code. We'll take the atmosphere and put it in a different set of code, and the surface water in yet another. And we do this even much more severely than I'm showing here. We literally have hundreds of different modules and subroutines in the code that separate the processes. So I'm going to go back just for a second and illustrate. If you know anything about long-wave radiation, every black body in the universe that has a temperature above absolute zero emits radiation according to its temperature. Stefan Boltzmann law and related laws describe what that radiation is. So the temperature of this cloud is determining how much radiation it's emitting. The temperature of my hand determines how much radiation it's emitting. And it's in balance with the radiation emitted by the surface. And so the surface is emitting long-wave radiation that propagates upward, it hits the cloud and warms the cloud up. At the same time, the cloud is propagating long-wave radiation that hits the ground and warms the ground up. And this is why you have warmer conditions on cloudy nights than on clear nights, is because the clouds actually warm up the surface. So the temperature of the cloud and the surface are actually very tightly coupled, but we don't solve them in most of our models implicitly. We divide them up and solve them separately, and they become kind of guesses at what the other one's going to do. So one of the ways forward is actually to do implicit coupling and higher level numerics in our models. Another thing we need to do is include more processes. We need to include things like cities, the way that people manage the land surface. We need to include the carbon cycle as well as water and energy. We need to include ice and snow, and we need to include things like vegetation dynamics. Our models, if they don't know how the land is managed, or forest fires or other kinds of systems, need to be able to actually grow and change plants as they grow forward. So this is the description of the community land model version 4, which some are saying is kind of the first or zero generation land component of a true Earth system model. And I helped to develop CLM, so I'm kind of proud to say that I think that they're on the right track. But they still have a lot of things missing and a lot of issues that need to be addressed in just modeling these processes in a comprehensive way. In 2011, Eric Wood from Princeton University and a group of us went to a workshop on hyper-resolution land modeling at Princeton and wrote a paper about it, Wood et al. 2011, and came up with a vision for what this would look like. And essentially, it would be a fully process scale resolving model of land surface hydrology, atmospheric dynamics, and cloud processes over the global domain that would actually work on scales of hundreds of meters. So it's a big challenge. And it would involve new kinds of land models that would link explicitly the surface and subsurface dynamics, groundwater and stream interactions. It would explicitly link land-atmosphere interactions, small scale. It would allow for small scale lateral feedbacks that you might see, say, in sea breezes. It might include water quality. It would certainly include human impacts such as urbanization, abstraction, diversions, land change. It would have computational considerations and considerations for allowing us to constrain, calibrate, and learn from new data. There was a response to this paper. So another scientist, a famous scientist from the UK, wrote a response. This was in Water Resources Research, and called this hyper-resolution ignorance. And there's a point to what he was saying, and we addressed it and agree to disagree. But essentially, if you go too high of resolution, you may not actually have any real information at the high resolutions. So we have to be careful when we're doing high resolution stuff that we actually are doing meaningful stuff at the resolution that we choose. And so you could run a model at 1 meter resolution, but what is the effective resolution of the information in that model? And we have to make sure we are, if we're running a high resolution model, we're actually running it for the right reasons and we have information to justify those resolutions. And that brings me to an idea I have, and I've actually talked to Bob this morning about this a little bit, and hoping to improve it. But one of the first things to get to these high resolution land models is we need to know what the atmospheric forcing is. So there's 7 basic variables that come from the atmosphere and force the land, hydrology and land processes. And those are things like wind, speed, and direction, temperature and humidity of the air, precipitation, and radiation, sunshine. And we need to know those things at these high resolutions. We don't have any networks that can measure weather variables at I'm targeting 500 meters here, sub 1 kilometer. We don't have any systems that actively can measure networks or observations at 500 meters of these variables. So, so we need an approach that will globally downscale. In this case, I'm looking at doing this in real time. So numerical weather forecast analysis first guess. This means the weather prediction centers like NOAA, NCEP, they bring together all the observations they can get their hands on, and they try to figure out what the current conditions are. And then they make their forecast based on that. I want to know what those current conditions are, the best available guess they have. And I don't want to know it just from NCEP. I also want to know it from the European Weather Center, which is proprietary and they want to sell it to me. But maybe I'll convince them at some point. But if I can use the highest resolution data to start with, and then temporally and spatially downscale, and I'm using idea that I'm calling physically based downscaling. So if you know anything about downscaling, the conventional wisdom is there's 2 different ways to downscale. One is statistical downscaling, where you use relationships or things like neural networks to train relationships. It's basically a regression between what are the relationships at the coarse scale and the fine scale. The problem is, like I said before, we don't know what the fine scale information is. So we don't have any way to train a statistical downscaling approach. The other way is a dynamical downscaling approach is to run high resolution coupled models at these scales. Well, if we had the computer power to do that now, we would be doing that. The computer power right now is limiting us to about 12-kilometer resolution globally. I'm a couple of order of magnitudes down from that at 500 meters. So it's going to be a while before we get there with using conventional models. So I'm stuck. I can't do dynamical downscaling and I can't do statistical. So I'm actually borrowing an old idea that we've been using in the LDAS world, the Land Data Assimilation System world, for many years, which are things like simple elevation lapse rate corrections. So we know when we go up a hill, it gets cooler. We also know when we go up a hill, generally the precipitation increases. You can refine that by whether you're upwind or downwind from the prevailing direction of the weather, whether you're on a, get the orographic corrections correct. You could also do slope corrections for radiation. So whether you're north-facing or south-facing slopes. Land use and roughness characteristics could be used to correct wind speed. There's a whole list of things that we could do. The other thing is this is a big data problem. So I want to do a 5-year hyper-resolution hourly 500-meter terrestrial forcing data set. There's 135 million kilometers of land surface on the Earth, excluding Greenland and Antarctica. I'm not going to worry about those. And that equals about 540 million pixels at 500-meter resolution. This data set, doing a quick calculation, is about 1 petabyte in size. That's just the data set. That doesn't include all the stuff that goes into it to create it. So it's a big data problem, at least at this point. So there's a bunch of data sets I identified I want to use from real-time atmospheric analyses that are currently available it's actually 13 kilometers from the GFS, NOAA GFS system. Precipitation products from GPM and merged products at higher resolutions. Radiation products from generally geostationary satellites. Elevation products, of course, and this is where we get some of our 500 meter or finer resolution because we have elevation products at 30 to 90 meters globally. We also have MODIS data at 500 meters, and that's really one of the motivations for that resolution is that we have a long record of land cover and vegetation indices at 500 meter resolution. We have other things like satellite air temperature and high resolution weather networks such as the DOE ArmSite or the Oklahoma Mesonet. We also have commercial like WeatherBug has a lot of observations, high resolution observations on school roofs and whatnot. So here's what I want to do. Spatial interpolation and temporal interpolation using these various different physical corrections, topography corrections, land use corrections, precipitation, terrain adjustments, roughness corrections, and then adjust variance for small scale missing high resolution variability. I want to then follow it up, so that's physical corrections by observation corrections. So I want to integrate any high resolution observations when available, do some quality control and uncertainty evaluation, and then I'm open, and I'd love to, Bob, now that you've seen this, maybe you have some other ideas on how I could incorporate other kinds of downscaling ideas into this. But it might not be perfect, but I want to at least, we need to get a start on this. And I have some partners in Europe and the European Center who are excited about getting started. NASA headquarters has told me they want to demonstrate that this summer in some SMAP validation they're doing. So I think we're going to get some traction on this in the near term. Okay, so the last piece that I want to talk about, how am I doing on time? Okay, I'm okay. Okay, so the last piece I want to talk about is data assimilation. So if you haven't heard what this is the major reason why we've had improvements in weather forecasts over the last few decades. We use data assimilation mostly in weather forecasting, but it's also been used in oceanography, and in the last 15 years or so, we've developed data assimilation in the land surface and hydrology. So without looking at all the cartoons and words here, I just want to give you a picture of what this looks like. So imagine yourself, I do a lot of driving, I already told you about that. Besides having my hands-free device, I like to drive with my eyes closed because I get tired and rest my eyes for a bit. So every few seconds, I'll open my eyes and get a glimpse of the road and close them again and get some more rest. And what am I going to do with that glimpse of the road when I get it? Well, if I happen to be drifting off the road, I'll steer the car back on the road and get out of the median, or maybe I'll see a car in front of me I want to slow down for. Well, that's exactly what our models do. Our models don't have any idea what the real world is doing. They're just some code running in a computer. And so every once in a while, if we give them a glimpse of the world from a satellite picture or some sort of a radio sound or some kind of a measurement of their system, they can get a glimpse of the reality, and we can kind of pull them back towards reality, because without that, they'll just drift off the road just like I will with my eyes closed. And so that's all we're doing with data assimilation is trying to improve the models in first guess or initialization. And we do that with some nice statistical methods such as Kalman filtering. And that's the main one we've been using for land surface. That's not really used in the atmosphere because it's a little bit too expensive. They mostly use variational approaches called variational data assimilation. So it turns out this all comes down to hunting down and figuring out how to deal with error. So there's error in the model that we can get. Sometimes we run an ensemble of models and we can figure out what the error is because the model tells us. The other thing we can do is we have an error in the observation. So the observation we get isn't perfect and may have registration errors or representation errors, all kinds of things. We need to account for those. And we put them together in a Bayesian format system of merging PDF information together and reinitializing the model. So this is actually some work I did for my dissertation. I still find it relevant occasionally. So I did this in Walnut Gulch, Arizona. If anybody's ever been there, this is Tombstone, Arizona. There was a gunfight there about 150 years ago. That's kind of famous. OK Corral stuff. And it's a small watershed at 150 square kilometers. And I modeled it at 40-meter resolution. So when I talk about hyper resolution and my colleagues say, oh, the models won't work at those scales, I said, 20 years ago I was running at 40-meter resolution with the same physical equations. The equations are one-dimensional for most of the land models. And so it doesn't matter if you run it at 1-meter resolution or across the entire country. It still works. So I ran this model at 40-meter resolution. This is an observation that was made from an airplane of soil moisture. And Tombstone, Arizona shows up here as actually an error. So there's sidewalks and roofs and things that the remote sensing algorithms didn't understand. And so it comes out as kind of an anomaly. There's some other anomalies and spatial errors here. This is the model run at 40-meter resolution. And if you can see compared to the observation, it's too wet. And so the observation is a bit drier. And so when I combine them together with four-dimensional data assimilation, I get some neat kind of qualities I'm looking for in data assimilation. One of them is I'm able to correct the model where I don't have observations using correlations. So outside the observation area, I know that overall the model is too wet. So I'm going to take the entire domain and make it drier. So that's pretty easy to do. But I actually did that weighted by how far it was from the closest observation. The other thing that happens is it looks at spatial structures, spatial significance, and the Tombstone Arizona area comes up as an anomaly and doesn't end up in the final product, which is very nice. Some of the other variations do show up, the variations that are kind of shown by the model, and it's a combination of the two. There's some things that are troubling, like here at the end, it looks like there's a dry, the entire end of this image is dry. And there's also a dry patch over here in the model. And what ends up is this entire edge of the watershed gets very dry. And it's hard to know whether that's real or not because it's extrapolation. It might not be real. Anyway, we've done this now with, over the years with soil moisture globally, snow cover, snow water assimilation, skin temperature. We've done this with groundwater and runoff, and we're starting to work on doing this with carbon variables, so not even water variables. And we've done a lot of theory development, really focusing on the development of ensemble Kalman filtering for hydrologic data assimilation. There's a bunch of things to do in the future. Land models are highly nonlinear, which is a problem for some of the linear assumptions in the data assimilation. We want to assimilate things like radiances. We want to link calibration and assimilation. We want to understand the potential of data assimilation to actually downscale. We've done some experiments on that. We want to have better land models that include more processes like river runoff, routing, vegetation, and carbon dynamics. I talked about some of that already. We want to assimilate all kinds of new data, stream flow, vegetation dynamics, groundwater, boundary layer structures in the atmosphere, evaporation, are all things we want to assimilate in the future. And we want to understand how they couple to the atmosphere. So there's a few more slides here about that. So hyper resolution, this is a system that I pioneered and developed when I was at NASA called the Land Information System. And prior to even 2005, when we won the Software of the Year award for NASA, we were running globally at 1 kilometer resolution with a homemade cluster that we built in the basement of a building at Goddard Space Flight Center. So these are just computers that you could buy off Amazon, and we put 200 of them together in a kind of a unique system. Supercomputers don't have this, where we had memory on each node and disks on each node, so we could run a little piece of the world on each one. And we were able to run at this 1 kilometer resolution, so you can see that you can see things like New York City, where in the 25 kilometer you can't see that. We've done some initialization of models and predicted rainfall. So this is a model initialized without lists. This is a model with lists, and this is observed rainfall. So we're just knowing that ground information better, we could do much better predictions of rainfall. This is for a 12-hour forecast. We've also developed a global version of this land data assimilation system, which I'm not going to go into, and initialized coupled forecasts on the 3-month time scale. And this is the observation. This is the LDAS initialized. This is without. And we improved the forecast greatly. So it turns out that these systems have popped up all over the world. And so we put together the first system, the North American LDAS system. But now there's LDASs all over the world in Africa and Australia and Europe. These are some examples of them. And the idea is in the future we want to patch these all together. So we want to get the data from all of these countries where they're using their very best precipitation networks, patch them together and get a better global picture. So that's my vision for what the future global land data assimilation system will look like. And then of course linked to water resource applications. This is some work I've done with the Bureau of Reclamation to link some of the NASA products and models with the decision support systems of the Bureau of Reclamation. I'm running out of time, so I'm just getting towards the end. My last slide. So my vision here is the ultra high resolution integrated water observation and prediction system, an integration of hyper resolution microwave water cycle sensors, ultra high resolution high performance prediction systems, advanced data assimilation and calibration, and decision support tools. So thank you very much.
In the philosophical part of what we are doing as modelers. And you have a figure where you show kind of the steps to follow in order to finalize with the fact that we need to solve problems, right?
Right.
As the final point. And that process, you go from observations, modeling, forecast, and answer the solutions. To what extent the current techniques and approaches that we are following, like reaching very high resolutions, starting from the low resolution, the global, into the very high resolution, is going to solve and really address the solution of the problems and when we would expect that to come. That's the first part of the question. The second part of the question, which is somehow related, is as we look into very high resolution all the time, because we find that that probably is the way that we can measure that we are progressing, we are missing somehow the feedback from the local to the global scale and how we can start looking into this multi-feedback and the multiple locations and how the interaction is. To what extent you think you are addressing that point, which is basically linked to the global water system after all, and how far we are to start articulating ideas about that.
Right. So the first question was kind of about how adequate our current models are for taking on these high resolution challenges. And I think there are aspects of our models that I'm talking about land models mostly, that are kind of poised for doing these resolutions. As I said, I've run some models at very high resolution, but there's other aspects like in the atmosphere, the boundary layer in the atmosphere, where when you try to solve the solutions for very high resolutions, you end up needing to also solve with very short time steps. And that's a big challenge, and one that I'm going to leave to the atmospheric scientists to contemplate. But it might end up just requiring gigantic computers in the future. But but in terms of land modeling, there's actually some efforts around the country to abandon our current like CLM process. In fact, DOE just kind of DOE for many years has been a big supporter of the NCAR climate system model, and they've just recently pulled out of that and decided to do their own thing because uh, I've talked to some of the managers that are making those decisions, and they feel like the kinds of questions DOE needs to answer aren't really going to be addressed in the timescales of model development that's going on at NCAR. And I don't think I can argue with that, but they want to include really advanced human processes. So they want to understand how economies are linked with, agriculture and water use and really kind of go end to end and have social dynamics included in some of these models. And they want to link more explicitly the groundwater systems because they're worried about fate of contaminants and that sort of thing in contaminated DOE sites. So big real questions, but they require different kinds of models. So I think we're going to see a combination. So the second question you asked was about how to take some of this high resolution information and couple it back to the atmosphere. And I showed you a few predictions we've made with WRF initialized with higher resolution land model information, and it gives pretty good performance improvement. It doesn't always, but usually it does. And I think I think in the future, in order to kind of get the clouds right, we're going to need to get high resolution processes and things like sea breezes and even small scale processes that happen between different land use conditions, where you can have, convection occurring over bare soil, and then you don't have that happening over vegetated soil on very small scales. We're going to need to get those right to get the clouds right, and so we're going to need to incorporate those high resolutions in our global forecast models eventually. So unfortunately, it's a big computational problem, and it's hard to visualize doing that right now. But if we're not thinking about it, we might never do it. So, I think that's what I'm geared towards. Other questions?
Other questions for Paul? If not, Paul, I do have a question. You talk about the launch of SMAP, tomorrow. I was just wondering if you have any advices for our UNL students or for our faculties, how they can be involved with this SMAP data, in terms of testers, users of the data. Do you have any recommendations so that our university can be really involved with this SMAP?
Yeah, that's a great question. So SMAP, the Soil Moisture Active Passive Mission, really the first real soil moisture satellite for the U.S. is launching hopefully tomorrow from Vandenberg Air Force Base, and there's a whole plan of validation studies that are going to be done over the next 2 years, and I'm not actually part of the SMAP team anymore, but I'm aware of what's going on. They're going to be doing some various aircraft flights over places like the Oklahoma Mesonet and the Armcart site. They're going to do some flights over actually the same watershed I did my dissertation on. They're going to do some flights over Walnut Gulch. And there's plans, Jared Enton at headquarters, NASA headquarters, is planning to do even more flights, maybe over Canada and the central US. And there's an opportunity for students to participate in the validation activities, the field components of that. So if you're interested in, as a student, in doing some field work this summer or next summer, let me know, and we certainly could use help. But further, the data will all be free and available. So that's the case for all of the NASA satellites for the most part. And so when it becomes available, there's a checkout period of a few months. I think they expect the first observations, real observations, to be kind of in the May or April, but mostly in kind of the May timeframe. And all of this is totally dependent on what happens tomorrow. In my experience with NASA satellites, is they rarely launch on time. So who knows? But apparently there's a window that if they don't launch really soon, then the launch might be delayed like a year because somebody else needs the launch pad. Some other mission of higher priority they'll have to take it off the launch pad, launch another mission, and then put it back, which takes time. So anyway, let's hope it all works tomorrow. But there's been a series of failures the last few years from Vandenberg, so keep our fingers crossed. It's also a very complicated mission. It's a awkward mission with a great big antenna, 6-meter antenna that's really about as big as this room that's spinning, and it scares me that thing is just going to spin off and not be heard from again. So let's hope that the engineers did their job and figured out all those dynamics. But it certainly is it's a big mission for hydrology.
Okay, let's show our appreciation to Dr. Hauser and give him a big applause.